So let's do this. The only thing I can do with this is square the whole thing. I can't simplify the radicals as are. So it's x squared plus 2 xy plus y squared. This is gone. 25 and 25 is 50. Put that aside. This is 2 times x plus y, x minus y, x squared minus y squared. So 625 minus 100 times 6 is 600. So 50 plus 2 times root 25. So 50 plus 2 times 5. So 50 plus 10 is 60. And I remember I squared it at the very beginning, but there's not actually a square there, so I have to remember to undo that process at the end. Take the square root of that. It's root 4 times 15, or 2 root 15. What's the units digit here? Okay, so this is, I just care about the units digit. It's going to be 7 to the 12th minus 3 to the 3 squares, 3 to the 9. So this is 7, 9, 3, 1, and this is 3, 9, 7, 1 are the patterns. So 7 to the 12th is going to land here. 3 to the 8th is here, so 3 to the 9. Now the trick is to look at which one is bigger. Do we go negative or not? In which case it changes it. You know, if I have something ending in a 5 minus something ending in a 4, that's something ending in a 1 if they're both positive. But if I have like negative 15 minus 4 or something like that, that's negative 19. That ends in a 9, so that'll actually flip it. It's very tricky. So I have to see, okay, do we go negative with this? In other words, which of these is bigger? Well, yeah, this second one is a huge number raised to the 9. That's going to be bigger. So basically I'm going negative. So I could do like an example problem, so this is 11 minus, let's call this like 13 as an example. Negative 11, sorry, 11 minus 13, because the second one is larger. That gives me negative 2. So the units digit is actually going to be 2 when we go negative. This is, okay, so I'm going to simplify this. 5 to the 5x minus 5 over 4 to the negative root y. Well, don't sweat the negative up in the, that just means do the reciprocal. Put the root y, 4 root y in the numerator. Now it's 4 to the positive root y. I'm also going to correct 5 to the 5x minus 5 into 5 to the 5x times 5 to the negative 5. Same thing. And then now I can do the reciprocal. That's 5 to the 5 down there. So I just need these two values. So if 5 to the 10x is 4900, 5 to the 5x, I just take the square root of that. That's 70. So this part is 70. And then 4 to the positive root y. So if 2 to the root y equals 5 squared, I need to square that whole thing. 2 to the 2 root y equals 5 to the 4th, or 4 to the root y is 5 to the 4th. So then I put that in. 5 to the 4th. And then that'll cancel, and then 70 over 5, it's 14. For this one, the value of 5, okay, so if I take out a 5 like I do with, same basis being added or subtracted, I realize I still have a mess in parentheses, So let me go back and just start to do this math and look for a pattern. So 5 plus 20 is 25, which is 5 squared so far, okay. If I add that to 4 times 25, 4 times 25 is 100, plus the previous 25 is 125 so far, which is 5 cubed, everything added together so far. So then 4 times 5 to the 3rd, so 4 times 125 is 500, plus the previous 125 is 625, which is 5 to the 4th, everything added together so far is 5 to the 4th. Well, okay, what's going on here? This is just going out 5 squared, 5 to the 3rd, 5 to the 4th. So the sum through here would be 5 to the 5th, and the sum through here would be 5 to the 6th. Looking for a pattern. So you'll see this. How is it possible for all of these odd numbers to multiply together to be a multiple of an even number? Okay, where does the even come from? I don't see it in any of those. Well, look at this. N is a non-negative integer. We've seen this word before. What's the difference between non-negative and positive? Why do they go out of their way to say non-negative instead of just positive? That means 0. The difference is that if it's non-negative, that could include 0. So that means 0 is the key to the problem. When there is a problem solving, data sufficiency, when you see non-negative, think 0. Because all of this could be a multiple of an even number or of an odd number. An even number can be a multiple of an odd number, right? If n is 0. Okay. So yeah, that's how it works, that all these odd numbers multiplied together end up being a multiple of an even number. N is just 0, so the 26 to the 0 is 1. That's how it. Okay, so anytime you see anything that seems to be impossible, with an exponent it could be possible if that exponent is 0, because then everything's just 1. And everything's a multiple of 1, you know? So then we know n is 0, so this is 0 to the 26 minus 26 to the 0. This is 0 minus 1 is negative 1. Okay, 6. Let me get the nearest fifth. So x to the fifth, or so 2 to the 5th is 32. So if I took like negative 2 to the 5th, that would be negative 32. So x equals the 5th root of negative 37. That means how does x compare to negative 2? Well, if it equaled negative 2, then that to the 5th would be negative 32, but it's all actually at negative 37. It has a greater magnitude. So x needs to be less than negative 2. Take a second and think about that. It needs to be like negative 2 point something for raised to the 5th power to be less than negative 32. So I know x is less than negative 2, so which of the following must be true? X greater than negative 2, no. X squared less than 4. That's not true, right? So when I square the whole thing, x is like negative 3, for example, and that squared is not less than 4. X to the 4th greater than 32, not quite. X cubed less than 8. That's going to be true. So I cube this whole thing. I get x cubed is less than negative 8. So I've got to approximate here. There's no way you can actually do these radicals. Root 3 is a little bit more than 3. Cube root of 9 is a little bit more than 2. 4th root of 8 is a little bit more than 1. A little bit more than 1. The trick is, from here on out, any power of anything greater than 1 is itself greater than 1. Okay? Any root of anything greater than 1 is itself greater than 1. Even if I have the millionth root of 2, that has to be bigger than 1, because 1 to the million is 1, the millionth root of 1 is 1. That's like a stopping point, okay? So these aren't less than 1, these are all just 1, let's call it. So if we add these together, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, it's got to be bigger than 12, because it's greater than 3, greater than 2, all these are greater than 1. Don't worry about 8 here. Just say everything else after the dot is just to make it equal to 3. A very tiny number, insignificance, that makes it a nice perfect square. 6 plus 3 is 9, square root of that is 3. 6 plus 3 is 9, square root of that is 3. Plus 6 is 9, square root of that is 3. 6 is 9, square root of that is 3. Don't worry about that. Okay, so it's closest to which of the following could factor out and then go from there. What something you may have noticed of every time you factor out and cross out the plus 1 or minus 1, it's the same as just crossing out what was originally being added or subtracted, because it would distribute back through. It's the same thing. So maybe as a shortcut here, being slightly less careful, but it's all good, is cross out what's being added or subtracted. Those are very small compared to like 22 to the 22x and 11 to the 11x. These are nothing compared to each of those respectively. So 22 to the 22x over 11 to the 11x. So I'm going to call that 2 times 11 to the 22x over 11 to the 11x. That's 2 to the 22x times 11 to the 22x over 11 to the 11x. So I can cancel 11x. 22x minus 11x is 11x, okay? So 2 to the 22x minus 11 to the 11x is what I'm left with. Don't worry about 10. Classic exponents in the exponent. So if x squared equals 64, or 2 to the 64, that means x equals 2 to the 32. Just taking the square root. And x is positive, so don't worry about the negative case. So then x of x is 2 to the 32 raised to 2 to the 32. That equals 2 to the y. What do I do here? 32 times 2 to the 30. Sorry, that's 30. How do I zoom in? How do I do 32 times 2 to the 32? Well, I do 2 to the 5th times 2 to the 32. So 2 to the 37. So that whole thing is 2 to the 37. So now I know that. That's as far as I can go with that. So y equals 2 to the 37.